Right on time, guys. And welcome back to another episode of Introduction to Computer Networks. Okay. So yesterday you hear about switching fabric in the router, right? So there are 3 different architectures. And you also hear at the very end of yesterday that there's this very special phenomenon called head-of-line blocking. That says the kind of memory you use at the input-output port determines also how efficient your switching fabric is. Okay, and the head-of-line blocking is also a good subject that connects us or transition us from switching fabric to talk more about the input and output port buffering. Okay, so today topic number 1 will be buffer management. First video is the overview of buffer management. Having a buffer, having a queue, we have actually 2 mechanisms that we actually need to design. Okay, one is called buffering, the other is called scheduling. So let's start with the overview video. Buffer management in the input port and output ports are the same, so let's just talk about the output port side. So what I'm drawing here is the detail of the output port. So yeah, it looks very much like the input port, except it's being mirrored. So we do have this one here. Yeah, this is where the buffer space is, and packet get queued up here. Okay. And this component is doing the link layer protocol. And therefore this one here, although called line termination, but this is where also the physical layer is implemented. Now let's focus on, buffer management here. So buffering is required because data could be coming in faster than the pace they'll be going out. Right? So when that occurs, we could, drop packets when there's not enough buffer space. So what's critical here is to decide how much space to allocate to the buffer. And in case we need to drop a packet, do we always drop the incoming one, or maybe we pick one of those packets existing here? Okay, because that seems to be a bit fair, right? Because the packets get queued up here could be coming from one flow. So the later flow, if we drop, from within the queue, then it will be more fair to the later traffic. Second issue is this. So the packets will be drawn out of the queue and get onto the outgoing link. Which one do we pick? Okay, one could actually start from the first one. One can also pick one of the packets seems to be more important and pass it out further. So, perhaps you could have some sort of priority-based mechanism so that the packets can be classified and some go out earlier than the others. Or we might want to maintain that it's fair. Okay, so we want to maintain neutral so the treatment of all these packets will equal. And the first part of the buffer management is this, determining how much space being allocated to the buffer. The documentation says this, the buffer space should equal to the typical round trip time multiplying the capacity. The intuition behind this is this. It has something to do with how TCP does the condition control. You see, in TCP, data being sent, X coming back. After receiving duplicate X or waiting for timeout, then the source will discover there's a packet loss, there's a condition, and therefore slow down. Right? So router in the middle there, is thinking, well, I'll need to buffer the packets long enough before the sources know they need to slow down. Right? And that is at least 1 round trip time. And during this amount of time, there could be this much packet or this much data going through the link here. So that's why RTT multiplying the capacity here. In this example, we have the round trip time 250 milliseconds and the capacity being 10 gigabits. These are very typical values, but you see also the amount of memory requirement pretty high, 2.5 gigabits. So not exactly practical. So some of the recent study actually discovered this. If all these flows going through the routers are TCP flows, and if there are n of them, we could actually reduce the buffer requirement to this amount. Still, RTT multiplying C at the top, but we can actually divide it by a certain factor. The more TCP flows there are, the more we could reduce the buffer space requirement. So n here are TCP flows, n flows here are n TCP flows. The reason for this is twofold. One being, TCP at the beginning is doing slow start, starting from window size 1. And the sending rate is very, very slow. And there are a lot of data we send over the internet being very, very small. And so we use a very slow rate to send small data. So most of these TCP flows run in the low rate. Okay, so we are actually not using the entire C capacity. Second is this. Even though we are in the steady state, okay, these window sizes are all pushing and dropping, okay, chances is also high that we are not using the full capacity as well. Okay, so still also low, but not as low. Okay, in the slow start state, sending rate really low. Even in the congestion avoidance rate, it's actually lower than the capacity as well. Okay, so that's why we come up with the factor here. The second component in the buffer management is this, the dropping policy or the discard policy. So this is needed when packet arrives to a full queue, right? So either the arriving packet needs to be dropped or one of the packets in the queue needs to be dropped. Okay, so generally, pick the next packet to discard. The most common policy is this, tail drop. So this is essentially just to drop the packet that is coming in the last, okay? Because usually those who arrive early are given priority. But you could actually change that, okay? Assign priority to the packets. Some of the packets might be less important, right? So we could classify them to lower priority. When a packet comes in with a higher priority, then we drop one with a lower priority. Third, random. Of course, one could pick randomly from the queue a packet being discarded, right? The last component is this. How do we debuffer? Okay, which packet do we choose to transmit next? Okay, so the next packet to send on the link. This is also called the scheduling policy. Typically, we do this FIFO. Okay, first in, first out. So essentially, based on the packet, based on the order the packet arrives, we take one out at a time. But one can also do this, the class-based scheduling. Okay, the way to do it is to divide the packets also based on the priority or based on the classes. Okay, and so we could assign a specific class being higher priority versus others, or we could have them rotating turns, taking one packet from each class at a time. And we can actually allow multiple packets coming from one class at a time, and so that there are more packets coming out from a particular class. It's sort of a combination. So weighted fair queuing here, WFQ, is a combination of the priority and round robin. Let's go into each one of these a little bit more. So priority-based scheduling. So we send always the highest priority packet out. Okay, so when there are multiple classes, okay, with different priorities, so we send out the one always with the higher priority. If there are no packets existing, then we take whatever we have. So here's an example. Packet arriving, some being red and some being green. Green packets are the one with the lower priority, while the red ones are the one with the higher priority. So the way it works is going to follow this timeline here. So a packet is arriving at this particular time, and there'll be some time it takes for the packet to be served. And then after they finish serving, packet exit. So let's say packet 1 arrives here. Right, so right there, packet number 1 being served, and it's going to take some time here. At this point, packet 1 will exit, but there could be other packet arriving while we're serving packet 1. So 2 and 3 arrives here, but 2 is carrying a lower priority, while 3 here carrying a higher priority. So in priority scheduling, which of these two, 2 versus 3, will be scheduled next here? Always the one with the higher priority, which means 3 here, right? And then next 2. Now, while we serve packet 2, if packet 4 arrives, right after packet 2 exit, we enter and serve 4, and so on and so forth. Now, if we do round robin, okay, the rotation-based, class-based queuing, we do have multiple classes, but we do the cyclical scan, okay, of different class queues and send one at a time. So the same pattern, 1, 2, 3, 4, 5 packet arriving at these point in time. But this time, okay, the second packet is higher priority, third packet lower priority. So which one do we send next? We actually send packet 3 because it belongs to the other class, not necessarily lower class, but the other class. We have to rotate. Therefore, after red packet is served, we serve the green packet. Now, because the next rotation is red packet again, so we take packet 2. Now, the next one should be green again because there's no green packet at all, so we serve packet 4, and so on and so forth. Last is the combination of priority and round robin, so weighted fair queuing here. Okay, so this is a generalized round robin, and it's almost like having some level of priority here. You assign weights to different queue. So way number 1, way number 2, and way number 3 here. Okay, so in one run, we could draw 2 packets out of the red queue, and 1 packet out of the green queue, and 3 packets out of the blue queue. Okay. In the second round, 2 more, 1 more, and 3 more, but because there's only 1 left, so we just get 1 more out. So this is weighted fair queuing. All right, so that was router. So we started by talking about the hardware components, and today we talk about how we manage these hardware components. So in terms of buffer management, you see that there's a formula to calculate how much buffer there is for a particular router. It depends on number of flows you might have, right? Of course. Also the capacity of the link and etc. There's also a buffering policy. That is when packets coming to a full queue, which packet do we drop? And then of course the scheduling policy. And you just heard that there are several ways of defining the scheduling policy. Next topic, very important. I think if you recall when we were talking about TCP or UDP, we spent also quite some time talking about the packet headers. This IPv4 packet format, we talk about the packet headers, but in the network layer. Because in the network layer, there's only one protocol, the IP protocol. Okay, it's best effort, connectionless. So this is the only header that you need to know, at least for IPv4. Okay, so the video is a little bit long, about 6 and something minutes, almost 7 minutes. But pay attention once, then you're done with it. All right, so let's start. 4.3, Internet Protocol. Now you see here, the section is a little bit long, so do expect that we spend quite a bit of time here. All right, so network layer is in the middle, okay, of the protocol stack. So what I'm showing here are, again, the important functions to be implemented there. Forwarding, we've already talked about in 4.2. Routing being in the data plane, we'll only talk about it in Chapter 5. Another thing we'll talk about in Chapter 5 is this, Icmp. This is one of those management protocols. So just like routing, management is also one of the control plane functions. So we'll be talking about Icmp later in Chapter 5. So what's left in Chapter 4 is just this, IP protocol. In there, we're going to talk about this IP addresses. If you recall, in forwarding function, the traditional model actually checks what? The destination IP address. So that's definitely talk more about the address format. Okay? And in the modern forwarding, we do what? SDN. We could actually look at multiple fields in the packet header, okay, to decide where to go. So we do need to know a little bit better about the packet format. What are the header fields? So that's coming right now. Now the 2 most important fields, source IP address and the destination IP address, each 32 bits long. Second, the header checksum. Now the reason this is important is because we did have what, TCP or UDP checksum that would ensure the integrity of this part of the packet. What about this part of the packet, the header part of the packet? We needed a checksum here, okay, to ensure the header part is also not having any bit errors. Now let's go over these individual fields one by one. So focus on the first one. First field, there is called the version. So the packet we're actually showing here is defining IP version 4. Okay, so the version number, therefore, will be 4 here, always. And then 2 other fields, header length and the length. So the header length here is to tell the size of the header. And the length here, telling the entire packet size. Last field in the first row, the TOS. Okay. It looks a bit familiar, isn't it? Because when we're talking about congestion control, there's this flavor called the network-assisted approach. So we did introduce one mechanism that requires the use of the ECN bits. So these are 2 bits in the IP packet header, if you recall. This is explicit congestion notification. So those 2 bits are right here, again, in the IP packet header. Now let's switch gear and take a look at the fields in the third row. Okay, first is here, time to live. So this field is very, very special. Okay, we've never seen it before, and it will probably make sense, only it's in the IP layer. Okay, so we would do this. We would decrement the value here, time to live, TTL, by 1. okay, after a packet passed through a router. Okay. When this value reaches 0, what we will do there, this router is going to discard the packet entirely. Okay. That is also saying a packet here, given n as the TTL, will only be able to hop n routers on the internet. Okay, and afterwards it's going to be just dropped. Okay, so time to live here is kind of regulating, okay, how many hops the packet can travel on the internet. And the reason we need this is because, on the internet, routing algorithms, okay, depending on how the messages are exchanged, depending on the computation process, we sometimes ended up having loops in the routes being computed. Now, in these cases, packets can actually travel the internet forever, like ghosts. Okay, so not good to have these ghosts, right? So let's set a time to live so that they're more human-like, right? So maximum number of hops the packet can travel. Second field in the third row, upper layer. Okay, so this is something that's slightly familiar because this is telling, okay, the network layer that after we extract the segment part, which place in the operating system we pass the segment forward. Okay, so the upper layer protocol, what is that function there? Okay, handling this incoming of a segment. Okay, so upper layer protocol to deliver the payload. It could be the UDP handler or the TCP socket handler. Now the second row. So these three fields in the second row are actually working together, okay, supporting each other. And it's for a very important functionality called the fragmentation and reassembly. The thing is that the IP datagram, when it enters the link layer, now the link layer actually defines a maximum packet size or maximum frame size. The packet in the link layer is called a frame. Okay? Now that size can very well be smaller than the IP packet size. So in that case, we need to cut a big datagram into smaller frames. Now these flags there, okay, are allowing us to reassemble the frames back so that we can recompose the original packet, original IP datagram. Last field, okay, here, the options. Now these are optional because it's usually for debugging purpose. For example, if we want to make sure that we track at which time point this packet travels through a particular router, we could have the router adding a timestamp here. Okay. If we want to make sure that we know the exact path this packet is traveling through, now each router there in the middle can sign here so that we know exactly which router, okay, this packet has visited already. Okay. Now, if you sum the header size together, okay, so each row is 32 bits, so it's 4 by each row, and we do have how many rows? 1, 2, 3, 4, 5 minimum, right? So that's at least 20 bytes. So the IP packet header itself, 20 bytes. Now we didn't count the TCP packet header explicitly, but it's also 20 bytes. Right? So that's at least 40 bytes of header, okay, in a packet. Now if we are sending data that's very, very short, like 3 bytes, 4 bytes, the overhead, okay, of sending data with large header like this can be pretty high. Okay, so one of the problem in IPv4 is that the packet header there contains fields that might not be really necessary. So later you will see in IPv6, they will try to make it as concise as possible.
All right, so that was the IPv4 packet header. So if Polly asks you, is port number in the network layer header, would you say yes or no? If Polly asks you, is the destination address, IP address in the transport layer header, would you say yes or no? Okay, but overall, you see that the IPv4 packet header, many of the fields look familiar, right? So you have checksums, right? You have IP address or port numbers, things like that, to identify a process or identify a host. But you see that in IPv4 packet header, there are also things that are unusual, okay? For example, time to live. That's very interesting. We've never seen something like that before. For example, TOS, type of service. Okay, so these fields are very specific for routers to indicate the status of the packet, okay, or how you like the routers to differentiate packets. Next, there's special row. I think it's the second row, right? We have 3 fields That's to support packet fragmentation and reassembly. Okay, so the next video is to talk more about that, because these three fields are also unusual. We've never seen something like these in the transport layer or application layer headers. And that video is also about 6 minutes. Okay, the mechanism of doing fragmentation and reassembly.
So that is the IP packet format. There's one thing we're yet to talk about, the fragmentation and reassembly. Remember the second rows of the header fields. So those fields are related to this function, fragmentation and reassembly of the IP datagram. The reason we need this is this. Okay, packets, as they travel the network, they might go over different network links. So for example, packet traveling the network like this. Now this could be an Ethernet link, this could be an optical link, and this could be yet another optical link, while this is another Ethernet link. So these packets might be going through different link layer technologies, running different link layer protocols. In those protocols, they might have different MTUs being defined. So this is the maximum transfer size, essentially the maximum packet size at the link layer. So different link types, different MTUs. Some of these MTUs can be smaller than the IP datagram size. In this case, we need to break the IP datagrams into smaller parts before passing out to the link layer. Now, some of you might be thinking, wait. Hey, didn't we do something like this in the transport layer, right? We take messages from the application layer, break the message into smaller parts, add the transport layer header, and that form a segment, and we pass it down to the network layer. At the network layer, what do? We break the segment into multiple parts, add the IP header, and then pass it down to the link. So why didn't we just do that, right? Because then at the link layer can just break the datagram, right, into parts and add the frame header, and such that it's smaller than MTU. Problem solved. You're right. It's just that the link layer protocols here, they are all quite primitive, and there's a good reason for that. That is because we do want packets to travel really fast on a link. So link layer protocol does not do the segmenting datagram implementation. So that's why the network layer there, poor network layer. The network layer needs to break segments apart for the transport layer. The network layer also needs to break the datagram apart for the link layer. So fragmentation reassembly is actually to do the link layer's job of breaking the datagram apart and reassembling them back. Now let's see how it works. A large IP datagram needs to be divided into multiple parts. When we run into a link that defines a smaller MTU. So one datagram will become several datagrams like this. Note that these smaller ones are not frames. These smaller ones are IP datagrams. All right. So we actually break them into multiple parts before passing it on this link here. Now these datagrams will remain the way they are through the network and comes into destination. The reassembly is only done here, only at the destination. So only the final destination is doing the reassembly. Now the breaking of the original datagram to multiple parts and the reassembly of the multiple parts back to the original datagram is relying on those three IP header fields. Let's go over an example to showcase the three header fields: ID, fragmentation flag, and offset. The example says we do have a large datagram for 1,000 bytes, and we're running into a link with MTU being 1,500 bytes. So let me show you the result, straight. So this large datagram is now fragmented into three smaller datagrams here. And so 1,500 is the maximum transfer unit size. So each, less than 1,500. You see there, the three smaller packets will all be carrying the same X. Yes, you are correct. So X is there. So the ID field there is used to identify which of these packets belong to the bigger datagram originally. Second field, you see the three are in sequence. First, second carries the flag 1. Only the last one carries the flag 0. So the one carrying the flag 0 is the ending packet, ending datagram. These two would both be carrying 1, saying that they are actually earlier datagrams. But which one goes first and which one goes second? You can actually look at the offset.
those carrying smaller offsets earlier. In fact, what the offset is saying is the position of the first byte here in the original data packet. Okay. So first byte here is the original byte 0. Okay. First byte here is the original byte something. Okay. It's not exactly 185. It's actually 185 multiplying 8. Okay. So the offset is actually counting 8 bytes at a time. So that is a way to try to make sure the offset field is a little bit narrower. Because then, one byte packet, that's just not making sense. Right? So there, you get it. This is IP fragmentation and reassembly. Okay. Oh, and by the way, okay, if you multiply 185 to 8, you get 14A0. And that is because of this. Okay. There's only 14A0 data bytes in the first packet. Because, hey, IP packet header is 20 bytes, so total length being 1500, data can only be 14A0, right? So as I mentioned, 185 is indicating the position of the first byte in the packet, but the position should be divided by the A. Okay, the original position divided by A will be the offset value. Therefore, offset multiplying by A, the original position.
All right, so that was the fragmentation and reassembly mechanism in IPv4, and that is to do the segmentation for the link layer, okay, poor network layer. Now, we come to a very important topic in chapter 4. It's called Ipv4 Addressing. So it's to talk about Ipv4 addresses, okay. The first video is to talk about the format. Okay. And then there will be 3 topics coming ahead to talk about, for example, how we assign an IP address to a host and how the IP address is hierarchical. And it's important that it being hierarchical to support routing, flexibility in routing. And also, we are running out of IPv4 addresses these days. So we have this very special mechanism called NAT, to try to create the sense that we have more than addresses we could use. Okay, so coming ahead first, the address format. And pay attention to this video because the quiz today, the first one, is coming right after this video.
IPv4 addressing. Well, it's actually quite simple because you guys all know, right? The IP address is 32 bits long, like this. And the way we represent an IP address is more. Take 8 bits at a time, convert it from the binary form to the decimal form. And separate these 4 numbers by 3 dots. So, an IP address. And we actually say that, hey, each machine here is assigned an IP address. Yeah, it looks like it's indeed the case. Okay, but no, that's not quite precise. An IP address is actually associated with an interface. So, each network interface requires an IP address. The tricky part is just this. Okay. A host here, okay, being at the end of the internet, at the edge of the internet, there's usually just one connectivity. Therefore, there's only one interface. Therefore, there's only one IP address. If you look here, routers being inside the core of the internet usually have multiple connections to the rest of the internet. Therefore, multiple interfaces. And you see here, a router can be assigned multiple IP addresses. So routers typically have multiple interfaces while hosts typically 1. Nowadays we do have 2. Okay, that's why the reason for that is because sometimes if we do have wire network access, then we can plug in to Ethernet, for example, conveniently. In case now we can still use Wi-Fi. Okay. So regular hosts, we do have 2 physical interface cards, but we use it one at a time. Okay, so this is an end systems characteristic. Now the core systems router, definitely multiple interfaces. Okay. And you see a little bit more clearly that the interface is the part that connects a host, okay, to a link like this, to a link like this. Okay. So bottom line, IP addresses are associated with interfaces, not a physical machine. Now, we did not print any of the links here, right? We did not show any of the links there. Okay, so how these interfaces are interconnected through the links. And we'll talk about the links in chapter 6 and 7. So this is the wired link and this is the wireless link, like this. Okay. This is the wired link, and a link layer protocol called the Ethernet. This one here is a wireless link, and it's the Wi-Fi protocol. Something else about the IP address you should have a rough sense about is this. You might have seen that the machines nearby, okay, the IP addresses for their network interfaces might look alike, especially the first, few numbers. So 223.1.1 seem to be shared by these interfaces that are physically connected. Yes, those interfaces that are physically connected to each other belongs to a subnet. So the first few numbers there, okay, is called the subnet part of the IP address. And the last, okay, that are unique, so we could separate the different different interfaces, is the host part. Those are the bits to the right, okay, the lower order bits. Now, only the interfaces that are physically connected, then they will share the same subnet address. So this is subnet 223.1.1. This is subnet 223.1.2, and this is 1.3. So each of them is a subnet, but these two are not in the same subnet because there's a router intervening. Now, we also use something like this to say, yeah, this is the subnet address. So subnet address. So you see here, this number is to indicate how long the subnet part of the IP address is. So A bits, A bits, A bits, 24 bits. Similarly, then the 223.1.2 subnet address is looking like this. And this is 1.3's subnet address. And what I'm teaching you here is there's an easier way to tell how many subnets we have here. Okay? Because if you want to assign the subnet address, if you need to decide how long the subnet part of the IP address is, you do want to know, right, inside your network, how many subnets there are, and inside each subnet, how many machines there are, or how many network interfaces there are. To determine the number of subnets you have, you need to detach each interface from its host or router. Okay? As a result, it's going to create an island of these isolated networks. So let's detach host, 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 router, host, 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 host. So we get what? One island of these network interface cards, one island of these network interface cards, and another island of the network interface cards. So each isolated island is a subnet. So if you want to figure out how many subnet there is for this network, break all these hosts and routers. Okay. So interface, physically connected, we have one up there. So subnet 223.1.1. We do have another one here, these three, and another one here, these three. And guess what? Another one here, right? These two together form an isolated island. Another here, and another here. So we together have 6 subnets here in this network. Until now, all these subnet addresses, we see this part being 24. But this is not quite true. Okay, to be more formal, the subnet part of the IP address can be arbitrary lengths. So the general format is looking more like this. Okay, the IP address on the left, and then an X, a number on the right. This indicates the number of bits in the subnet part. So in this example here, we do have the subnet part being 23 bits long. Say the blue part, only 23 of them. Therefore, the host part, we get 9 bits. So we could accommodate up to these many individual hosts. We could allocate these many individual IP addresses to these hosts. Now, if you have a subnet, that has a number of machines, higher than this, you will need more bits. So this guy here might need to turn black, and we need to use a length of, for example, 22. Now, one last thing to talk about is this. How do we write the ABCD out? So this is how it works. Take the IP address in the subnet, and then convert them to binary form. Write it out. And then cut that IP address right at the part that's separating the subnet and the host part. So essentially, cut there right after the 23rd bit. Turn all the host part of the IP address into 0. And then convert this octet back to the decimal, this octet back to the decimal, the whole octet back to the decimal, and then the whole octet back to the decimal. So if you have an x here smaller than 24, then this last number here is always going to be 0, right? Because it's always cut earlier here. All these bits will be 0. Therefore, this is 0. Now, as to whether this is going to be 0, well, it depends on, the subnet part. It could happen that all these, the subnet part is also 0, then you have 0. Okay. Otherwise, you're just resetting only the host part to 0 in order to write the A, B, C, D out. That takes us to an exercise.
All right, so this is quiz 32. That's exercise CIDR, the classless interdomain routing IP addressing. So on the side, you see at the top, it's the exact example we saw in the video. Okay, so it's subnet part being 23 bits, therefore the host part being 9 bits. And how do you write the A.B.C.D out? Well, you turn all the host bits to 0, okay, and then convert them from binary to the decimal, and 8 bits at a time. So we have 223.16.0, right? And we know already from the orange part that's 23 bits, so /23. And quiz 32 is to ask you to write the CIDR address for this example at the bottom. Okay, so what should be, we see A is 200, B is 23, obviously. What is C? What is D? And what is the net mask length? All right, so go to the Slack space, and there's a channel, W12, I think. W12 and quiz 32. Oh, wow. Okay. I thought there's gonna be some delay from Polly explaining the slides to you guys. Finally hear the question, but okay, very fast. So this is W12 quiz 32 channel. Team 5. That's just too fast. Are you right? So let's see. The A and B should be okay, right? And C is 01010000. 1, 2, 4, 8, 16 plus 64. 16. It is 80. Wow, cool. And then the last D should be what? D should be 11000000. So that's 128 plus 64. It's 92 and /26 bits long for the subnet part. Very good. Yay! Team 5 is the first to answer correctly today. Ke is also very fast. Great. Cheng Rui, perfect. Howard and Yu Jie, I guess, I guess this is a quiz that's typically too easy for our EE students. All right, great. So you get the idea, CIDR, how it's calculated. So later on, if you see on the internet information about setting up your own IP address, you see net mask, okay? That's 28 bits long. Sometimes, or 26 bits long, or 24 bits long. Sometimes it's written like this. If it's 24 bits long, it's written this way. Would you like to guess why? So this is actually net mask 24 bits. And
And when you're configuring your network, they might also tell you the first hop router's IP address being something like this. Yeah, so it's all in combination. First hop router 140.112.42.1. NAND mask 255.255.255.0. What this meant is that the CIDR address for the subnet is this. It's exactly this. Yeah, so if you write the IP address of the first hop router out in binary form, okay, and after you see this, you know that the NAND mask length is 24, because if you write 255.255.255.0 out, you see that there are 24 ones and the rest of them 0. Okay, that's another way to represent the net mask length. Okay, now if you write the IP address 140.112.42.1 out and mask the first 24 bits and use and set all the remaining bits 0, that's how you get the ABCD, and that's how Poly wrote 140.112.42.0/24 as the subnet address. All right, good. So that should be very clear for you guys. CIDR addressing. Now let's move on to the very important topics related to addressing. First is DHCP. Wait. Okay, so we do have a little bit of time before we take a break. So first is DHCP. Okay, this is the mechanism we use almost every day, and probably multiple times every day, to try to get an address automatically configured to our machine. Okay. Let's hear the introduction of DHCP first.
Let's talk about how a host gets an IP address. There are two ways, especially in the older time. You have to talk to the system admin first. System admin is going to give you the IP address, and then you manually type up the IP address at the specific place in an operating system. Now, how you do that can change from operating system to operating system. Where you do it exactly could also vary within the operating system from version to version. And some of you might need to reboot the machine as well in order to have the IP address taking effect. So this process here, the manual approach, very tedious, out of fashion. More fashionable today is to run DHCP, the Dynamic Host Configuration Protocol. What it does is to get the host and IP address automatically and configure it automatically. The service is entirely plug and play, so there's no manual effort required. Really nice. And we're using it every day. This DHCP protocol is already part of the protocol stack and part of the operating system, part of all the operating systems these days, including the mobile phone operating system. So formally, let me introduce DHCP. It allows us to acquire IP addresses dynamically. So what happened there is that our side of DHCP is running the client process. The subnet you'll be joining. The server process is running on the subnet, running on one machine on the subnet. So the two sides, client server, will negotiate and reach an agreement. So that agreement is actually a lease on a specific IP address. And that's why my host here gets to use a specific IP address. So with this, we bypass needing to communicate with the system admin, a real person. And the assignment is also automatically done because it's all part of the operating system. But essentially, after the negotiation, we get to use an IP address. But as you see here, it's a lease, meaning the IP address is also temporarily allocated. So that is why it's called the dynamic host configuration process. It only runs for a while. If you leave the subnet, this IP address will be reclaimed by the server. But don't worry, as long as you stay in the subnet, stay connected, stay on, then you get to reuse the IP address. And this is done by exchanging messages again between the client and server
So there are some more messages being exchanged and periodically so that we could renew the initial lease. So that is generally how the DHCP works. You see, this is really, really nice for us living now a very mobile lifestyle. Okay. And the process is very simple. This negotiation process is very simple. A very simple four-way message exchange. Okay. And an even simpler version is just two-way exchange. Okay. So these two first messages, they can be actually bypassed if the user is coming in and out really fast. Typically, the OS on a smartphone implements more this version of DHCP. Now, let's take a look at the scenario and go through these four messages in a bit more detail. So here it is. We've used this network already earlier to explain, right, what's IP address format and what is the subnet address. So let's assume we set up a DHCP server here connecting to 223.1.2 subnet. And we carrying a laptop, okay, running an operating system with the client process already running. So the arriving client process here, server process here.
All right, so next video, the detail of that scenario.
First message, DHCP Discovery. What it does is the client asking, in a broadcast way, is any of you guys the DHCP server? So if we look into the packet, you should see the source looking like this, a null IP address. And the DHCP client is default on port 68. The server, on the other hand, on port 67. Destination will be going to the DHCP server. But hey, the client doesn't know if there is a DHCP server in the first place, not to mention the exact IP address. So we're sending it to here, the broadcast IP address. A message carrying such an IP address is going to be received by all hosts on the subnet. Therefore, DHCP server being one of the hosts on the subnet will definitely receive the discover message. Why I address here? This is the field to store. The IP address potentially will be assigned to the client. Now, the client has no clue, therefore, it's null. Last is the transaction ID. Now, this is actually quite critical. Usually, it looks like a random number. Okay. Different clients will actually send discover messages carrying different transaction IP. Now, these IDs are also to tell the arriving clients apart. So there could be other clients arriving as well. And they could be sending these DHCP discover messages about the same time. Servers sending responses, DHCP offers, okay, about the same time. How does this guy know which offer is for this guy, and how does this other guy knows, right, which offer is for it? So transaction ID, okay, typically different, coming from different clients, to enable the clients to tell whether the reply is coming for the host or not. So very important. And to respond to the discover message, the server sends the offer message. Okay, so this is saying, I'm here. And here's an IP address you could use. And inside the offer message, you see the source being the server's IP address. Destination, again, the broadcast address, because arriving client doesn't have an IP yet, but will still receive a message going to the broadcast IP address because everyone on the subnet will receive such a message. And we see here, the server is offering this IP address to the client. Transaction ID, the same pair. Okay, so this offer is for this discover message. And you see, server here, while offering a specific IP, is also saying, hey, client, you get to use this IP address for 3,600 seconds long. Okay, so it's the duration of the lease. Client then say, DHCP request, okay, I'm going to take the IP address, and this is the content, asking for this IP address. And it's a new transaction for this long. In return, the server sends back ACK, okay, which is simply saying, okay, you got it. Okay, therefore, you see, you got the IP address for this long. And this, again, corresponds to this, okay, not to be confused with other clients requesting for other IP addresses. So this is the exchange of the four-way messages, okay, in DHCP service. Now, in the exchange, DHCP server actually say more, okay, not just the IP address, but a whole bunch of other things that are very critical setting up, okay, the subnet on the hosts. So first is who the first hop router is, because the host message is going out onto the subnet. The default next hop is always the first hop router, because the first hop router then, after picking up, then can determine where else to forward it further. Another important information, DNS servers. This is very critical, right? Because you are requesting www.google.com or www.something, okay, by the name of the server. Okay. In order to know the IP address, you also need to configure on your host the DNS servers. I know some of you might have some DNS server IPs assigned already, configured already, but if you connect to DHCP server is going to also add some IP addresses into that part of the operating system. Okay, so the name and the IP addresses of some DNS servers by default. And then the network mask. So this is to tell the host how long is the subnet part of the IP address. So provided the IP address, the DHCP server is also saying that, hey, what is the subnet part? And therefore, the client also know what is the host part.
All right, so we ran over the lecture time just a little bit, but it's okay. I'm going to give you back 10 minutes of break. So we'll resume the lecture in 10 minutes, which is 11:21. Okay, let's break.
right? It's 11:21. So essentially from the last two videos, you hear that DHCP is to allow a host coming into a network to try to get an IP address automatically. It can be done using a four-way message exchange, or in case you're in a hurry, in case the host is in a hurry, two-way exchange is also possible. Okay. And after the exchange, the host not only get an IP address, it gets also what? The first hop router's IP address, the NAT mask. The two together, you can what? Infer the CIDR subnet address. So you know which part is the subnet address and which part is the host address. And the DNS server, because it's the first thing that every application needs to do, needs to query pretty much, unless you know the IP address directly. Okay, so DHCP there we use every day. The next video is to present you what you will see if you actually sniff the message exchange in this DHCP protocol. And you'll see also all those things we just talked about. Hey, two-way exchange, four-way exchange message format, and the information, okay, that's hidden in these messages that allow the host to know the first hop IP address, the net mask, and etc. So this is video number 3 regarding DHCP, and right after this, quiz number 33 is coming up.
And to illustrate, you see in this DHCP example, host is right here, okay, we just joined. And DHCP server is already up, and it happens to be running on the first hop router. So what happened there is, the connecting laptop is going to send a DHCP request message out to the network. So this is the simplified version of DHCP. Sending request and server sending ACK. So the laptop here is asking for its IP address. In addition to that, first hop router, DHCP server, and netmask. So DHCP is actually right here, an application layer protocol. And that DHCP discover or DHCP request message is going to be what? Passed to the UDP and adding the UDP header, push down to the network layer and adding the IP header, and push down to the Ethernet and adding the Ethernet header and trailer. So the DHCP request gets encapsulated into an UDP packet, further into an IP packet, further into an Ethernet frame. So you know DHCP is actually implemented at the application layer. Just like DNS, seemingly a lower level functionality, a general functionality, okay, for everyone on the internet, but implemented at the application layer. Complexity at the edge. And it's using UDP as the underlying transport layer service. Now this frame, okay, carrying destination address being broadcast 255.255 all the way, is going to reach all the hosts on the subnet. So this is the entire subnet. By the way, this is an Ethernet switch. It's a rectangle, not quite a circle, so this is not the router. Okay, so this is actually the link. Okay, so this interface and this interface are connected through this link. So every host on the subnet is going to receive the DHCP discover message. So therefore, the server here is going to pick it up. So this is what going to be extracted, okay, and passed up to the IP layer. This extracted, passed up to the UDP, and this extracted, and eventually reaching the application layer. So the server then can see, this is a request message, therefore send back a reply. So you see here, going all the way, Ethernet gets demuxed to IP, to UDP, and finally, server side of DHCP. Now the server then will generate the ACK message containing the IP address of the first hop and the IP addresses of the DNS servers, and so on and so forth. So process is very similar, encapsulate to UDP, encapsulate to IP, Ethernet, and destination address being broadcasted. The host here, although not having a specific IP address, is going to pick it up. So the client now knows the IP address of itself, name and IP address of the DNS server, and the first hop, as well as what? The network mask. So what I'm showing here is the result of sniffing DHCP messages. This is a DHCP request message, and this is a reply of that. Earlier we actually called it the ACK packet, okay, ACK message.
And I can use tools like Wireshark or TCP dump to sniff packets travel the internet. Now, after sniffing, you're gonna see the content inside the packet. So what I'm showing here is, this is the request message. So you see boot request. And in the reply or in the ACK message, you see it says boot reply. And you see transaction ID, transaction ID, and they're identical. So this ACK here is for this request. And then you see also specifically the client not having an IP address, but it still have a MAC address. So that MAC address is actually hard-coded into the network interface card that came with your machine. Okay, so that is already existing. And that is something that the DHCP client is going to send to the server. So server can identify you somewhat by the MAC address. And then, this is DHCP request, okay, and this is DHCP ACK. And the client is asking for these, right? So the IP address, okay, so IP address is not clear yet. So requesting, this IP address. Okay, so this is not a sure thing. It's just that the client suggesting, can I get this IP address? And it's also asking for domain name servers, and the subnet mask. Server here, in the response, you will see, okay, hey, client, okay, it's okay to use this IP address. Go ahead. In the meantime, it's returning also the subnet mask, the first hop router, as well as the IP addresses of the DNS servers and the domain name. So all these information, client can then set everything up and then begin to access the internet.
All right, so given enough detail, then here comes quiz 33. Okay, so this is one of the interesting quizzes, fun quizzes, open-end problem quizzes. So the title of it is Taipei free, although being free, but useless. Okay, so this is a news report that probably extracted from the newmobilelive.com media. So I think it's a sort of a web media, okay, web news. The original articles is in Chinese, so don't worry, Holly has already translated it for you. So if we look to the right of the slide, what the news says is this. There are quite a few these free Wi-Fi access points all around Taiwan, particularly in the train station, airport, or sightseeing spots, things like that. So these are provided as a kind gesture to the travelers. But there's a survey being done by the newspaper. They find that 40% of the users are not exactly satisfied with the service. Okay, so out of 10 users they ask, 4 says no, they are not satisfied. So if they ask something like 100 users, 40 of them say they're not happy with it. Okay, but they dig into and ask these users who are not satisfied with the service why they are not satisfied. Okay, so 70% of these users say this. Well, we try to connect, but we are not able to connect to the free something at all. And only like 60-ish% complain about, they managed to connect, but the speed is not good. The signal is weak, or other issues. But the most complaint is that they tried to connect, but they couldn't connect. Okay, so Q1, grab your teammates. Okay, discuss. So what we are looking for here is genuine answer. Okay, so why? What's causing it? What's causing the trouble? How come these 74% of users not being able to connect to the free Taipei or free CHT service? Q2. Okay, once you know what is the cause, how can you remove the cause? Meaning addressing the problem such that there'll be fewer people complain that they won't be able to connect to the Wi-Fi, the free Wi-Fi. Okay, and this is an open-end problem. So try to think, hey, DHCP, IP address space, IP address format, all these things that we just talked about.
We have 10 to 15 minutes here, depending on whether some of you guys have already started posting solutions, okay, and whether there's a good diversity already. Let's set it to 15 minutes and see, okay. Take your time, okay. You do want to figure things out yourself. I don't know about you. If you read previous semester students' solutions, you are kind of influenced by them. Okay, you don't know when it's exam time whether you will be able to come up with your own solution, not being able to copy from other students. Okay, so it's always better that you can think about it and see if you come up with your own solution. Previous semester students' solutions are great, but you look at them after you figure things out yourself and you can validate, okay, whether you are thinking the same as the previous semester students. You might be thinking differently, and there's nothing wrong with that. That's even better because you come up with more potential causes and therefore more ways to try to address the issue. Okay, try to do that. I think you might feel better and learn more this way. Okay. Let's take our time. Go to the Slack workspace, and this quiz is W12, quiz 33, okay, in this channel. And let's begin. think I see some of the teams are still typing. That's great. That's great. I can feel that you guys have probably some fun solutions you want to share with us. So feel free to keep on typing, and let's see what are the what have been provided as answer to Q1 and Q2. The first is Team 10. Okay, so they find the problem that 74% of the users not being able to connect to the network at all. Is because the number of IP addresses do not satisfy the need of the users. Okay, so I think meant there are just too many users asking for IP addresses at the same time, and there's no more free IP address in that subnet. Okay, so every Wi-Fi AP creates a subnet as well, and a very typical default setting is to have 24 bits net mask length. Okay, so that means only 2 to the power of 8 IP addresses allowed to assign to individual hosts. Okay, and that's actually not many, about 200, and to be exact, 256 IP addresses at maximum. So if this is a Taipei train station, Taipei station, or the airport in the rush hour, we easily have more than that amount of users who might be asking for IP address to connect to the free Taipei or free Taipei station subnet. Okay, so yeah, so short of IP addresses, okay, in the subnet, it is one of the causes. Okay, if this is the issue, short of IP address, would build more DHCP servers for that subnet be helpful? But if you think about it a little bit more detail, if the issue is that you are short of IP address space in that subnet, the solution should be what? To increase the IP subnet space, isn't it? And to get more IP address. So DHCP server, if we have more of these servers for that subnet, it's still assigning IP addresses out of the same subnet. You see, because it's the same subnet. Yeah, but I think or Team 10 probably meant maybe we can create multiple subnets, okay, all being called free Taipei or free Taipei station. Then you can have a different set of IP address for each subnet. Then you can accommodate more users asking for IP addresses. All right. Does that make more sense? I hope that makes more sense, right? So you provided a reason, then you want to address address the issue because you see that cause or that reason that's causing the problem, right? Let's see Team 10, but hey, I think this is the cause is perfect. Okay, it is short of IP address is indeed one of the major cause that we don't get connected because we don't have IP address at all to get on the subnet. Team 5, the number of IP addresses is limited, so the Wi-Fi subnet may not be enough. Sure. Oh, okay. Team 5 provides an interesting solution, which we have not yet talked about. But Polly actually mentioned NAT a little bit earlier to say that it's a way to kind of pretend such that we have more IP address. We create this illusion that we have more IP address. Yeah, so you know the problem is that we are short of IP addresses. We need to expand the IP address space. So NAT does help. But to set up NAT, it's also a little bit tricky. Okay, I would say that Wei Xiang, your solution will work, but it will be a harder to implement solution. All right. Great, good idea, very unique. And Sean here, IP address is overload because too many try to connect at the same time. Yeah, so this is similar to what Team 5 and Team 10 have mentioned the cause. Increase the number of DHCP server. Yeah, this is pretty much identical to Team 10's solution. Okay, so I would just skip this. And, sorry, I meant to check Team 1's solution. So Team 14, oh, this is nice. We have multiple causes. Great. First of all, the DHCP server has already used all the IP addresses. Yeah, so no more free IP addresses to assign to other hosts, other users. Okay, this seems to be an obvious cause since this quiz follows the DHCP videos. Distance being to connect is too short. Okay. So maybe the request for IP address message and reply for IP address, these messages might have trouble being transmitted or received correctly because the user is too far away from the AP, right? So that the request message don't get to the DHCP server correctly in the first place. And this is not because this subnet DHCP server runs out of IP address. It's because these DHCP protocol messages having trouble, okay, getting to the clients or getting to the server. Okay, this is a very interesting point. When the client's distance is too far from the AP, yes, we will have trouble getting a packet through. Okay, and this is also often why even you are connected, you don't see the speed being reasonable to, for example, watch a video. Sending a line text might be okay, but not watching a video. Devices 2.0, well, I think devices 2.0 is probably related to the communication, wireless communication distance. Yeah. So usually the newer device uses newer protocols, newer standards. Usually the communication range gets improved. Bandwidth too low. Yeah. So this is essentially the outcome of this. Okay. So bandwidth being too low is actually the outcome of the distance being far away. There's another reason, however, that the bandwidth might appear low, which is having lots of users trying to send data on the same wireless subnet. Yeah, because there's only a certain capacity. The more are trying to send data, hey, the subnet gets congested. Yeah. So let's see what Team 14 has being the solution. I need more budget. Yeah, so you can buy a better device so that the communication range can be longer, or the wireless link capacity can be higher. So for example, upgrade from AL211 AC to AL211AX. Adding servers, buying new devices, increase bandwidth. Yeah, so these are essentially obviously what we will do, but how you implement them are the things that we're looking for here. Okay, let's see, 召集. The amount of users vary a lot. When some users just left the area, they don't need free Wi-Fi anymore. Their IP has not been released. Oh, it leads to some waste. Interesting. So this is saying something slightly different from what you guys have been saying, or the other teams have been saying, short of IP address. Team 2 here has a unique opinion. It's not exactly that there's not enough IP address. It can be because people come and go, right? As you walk through Taipei Station, you might walk, right, in just 10 seconds away from one subnet and enter another subnet. But you have already acquired an IP address from the previous subnet. And 10 minutes later, you're gone. Okay, but that IP address is allocated to you for a period of time. How do we call that? Yeah, that's called the what? The lease time, isn't it? In the examples you saw, 3600 seconds. Yeah, that's actually a very typical default value. Okay, that is how long? 3600 seconds. That is what? 60 minutes, which is what? 1 hour. That's pretty long, right? For many of the mobile users, this is probably not necessary. Therefore, Team 2 says that's shorten the lifetime of these leases. Yeah. So this will be the shortening the lease time of the IP addresses. Very good. Providing a unique cause and providing a solution that targets and remove the cause. Very good. Let's see. Metal. This is the best set of solutions probably seen so far. Okay. Let's see. Let's just go over one more team and then we'll come back to the lecture. Okay. You see that is probably try to adding. You see that providing a cause, addressing a cause. It can be a little bit superficial, but it can also be very targeted, effective. Okay, so solutions can also come in different level. Okay, and people appreciate always the more targeted solution. There are too many clients connecting to the internet at the same time. Okay, so I think this is the same as the previous teams, but previous team were saying that they are running out of IP address. Team A adds also, if there are so many clients and DHCP requests at the same time, it congests the server. Yeah, so this is a slightly different cause of users not being able to connect. Okay, not because of out of IP address, but because everyone is asking at the same time. So let's see what the solutions are. Okay, when the user occupies too large bandwidth, throttle the okay, interesting. This is very interesting. So this is saying that if the DHCP server says some particular host is asking for IP address continuously, this can potentially address a denial of service attack to the free Taipei subnet. One can actually write a program to ask for IP addresses and exhaust the IP address space. Then Q2 solution from Team A here will be very effective to prevent a DOS attack like this, right? So if you see from the MAC address, so MAC address we won't be able to talk about. It's a link layer notion. IP address is to identify a unique host in the network layer. MAC address is to identify a unique network interface in a host. A host could have multiple interfaces. So if the DHCP server here sees too many requests coming from the same host, same MAC address, same network interface, they can throttle this user. Yeah, they can throttle this user and therefore free the bandwidth up and allowing users that are really in need of having an IP address to get through and reach DHCP server. Okay. The IP address issue can try more servers, shorten the lifetime of IPs. Yeah. Okay, so this is slightly different, interesting, unique. All right, so short of IP address space, congestion at the DHCP server, too long release time. And for each of these, you know how to address it, right? So to address the IP shortage, the subnet IP address shortage problem, another way is what? To use a shorter network mask length as well, right? Then you get more host part of the IP address. It's a little bit harder to implement that solution because you need to make sure that you have that set of IP address. And real IP addresses are not cheap. But nowadays, these Wi-Fi subnets are all by default behind net. Okay, they are virtual IP addresses. So it's actually very easy to reconfigure a Wi-Fi subnet such that you use a shorter network mask length, and therefore you have more IP address space. All right, good. Now we move to the next topic, hierarchical address. You saw earlier already that the IP address has the subnet part and the host part. Okay, and it's already some sort of hierarchy. But that's not only it. Okay, that's looking to the introductory videos of hierarchical addressing. Okay, this is very important so that it helps routing.
The goal, so that was how a host gets an IP address. We ask the system admin for one or Dhcp server for one, which is configured by the system admin. So the bottom line is, how does the system admin get a block of IP addresses so that the system admin can assign to individual hosts? So the next question we're asking is exactly that. How a subnet gets the subnet part of the IP address? The answer is quite straightforward. As we ask the system admin for one, system admin asks the higher level system admin for a block of IP addresses. So if we are customers of an ISP, we ask the ISP for the address block. So what I'm showing here is an example. ISP owning a big block of IP addresses. Okay, so by big block, this is how big a block is. Now the prefix of the subnet address of the ISP is only 20 bits, so only up to here. Therefore, that allows us a bigger free IP address space. Now, if there are 8 customers, okay, subscribing from the ISP, organization 0 all the way to 7, ISP can further divide the bigger address space this way, extending the prefix by 3 bits. So that is pushing it further here. So 3 more bits being included into the subnet ID. Because there are 3 bits, so we could uniquely separate the 8 different organizations. But as a result, we get what? Less free IP space. Each now gets only this much. That is what? 1/8 of the original space. So we are splitting the IP address to 8 equal weights. And it is done very easy by just simply saying this, extending from 20 to 23. Let's say if organization 7 here having 4 departments and each ask for an equal share, then very straightforward, right? Extend from 23 to 25, the prefix lengths. And so we'll be actually doing something like this. Take 2 more bits here, and there are 2 bits, therefore we could identify 4 departments uniquely. And the IP address space is now down to 2 to the power of 7, okay? 1/4 of the second level organization here. So you see, using the prefix there, by sliding it to the right, we actually create also a natural hierarchy in the IP address space and dividing the IP address space. Just like how human beings divide and organize bigger society to smaller society and even smaller society. So this type of addressing, the IP addressing, is also called the hierarchical addressing. There's actually one more benefit of it, not just that dividing the address space is made very easy, but also this. We could do very efficient route advertisements. Now, routing is one of the major functionality in the network layer. We have not yet talked about it, so in order to explain how efficient this is, let me just give you a slight overview of routing.
Okay, so in a nutshell, the IP address can have not just one level of hierarchy, subnet host, but what? Subnet and a sub-organization in the subnet, and then sub-organization in a sub-organization. You can have multiple levels of hierarchy. All right. Now the video to give you an overview of routing.
The goal of routing is to form these forwarding tables, if you recall, right? Destination IP and outgoing interface. Now the way these entries are formed is this. If this is a destination, if somebody else on the internet wants to send data to this guy will need to announce its IP address, okay, in an advertisement and travel through the network like this to outside. Okay? That is how the router here discovered, oh, okay, I see a destination potentially this way. So that IP here and the outgoing interface is this guy here. Now for a guy, okay, who's connected to the internet this way,
that advertisement will go down, this other interface. So this other guy here, IP prime, the output interface will be linked here. So that is the general idea of routing. But then you see, for each machine here having an IP address, in order to allow other people sending packets to it, they will each need to send an advertisement announcing its IP address. Okay? And there are these many different IP addresses possible, so potentially worst case, right? Lots of advertisements each of these organizations need to send and travel on these links. And you know what? The most scary thing is this. All these need to go out to the internet, so the ISP needs to send these many advertisements. And that is just not going to scale. Okay? That will be a lot of bandwidth consumption just to send the advertisements. The solution is actually related to the forwarding mechanism in the router. If you recall, instead of listing individual destination IP here, rather we do this individual prefix, okay, and then outgoing interface. So when a packet arrives, the destination IP address matching the prefix, then we send it out on the outgoing interface. You know what? Isn't this a prefix? Isn't this a prefix? So what we're doing, in fact, in the internet is not to send individual IP address in the advertisement. We send an individual prefix in the advertisement. So what's happening there is the prefix in the advertisement gets here. Router here, receiving it, pass it down further. Router here, receiving it, pass it down further, but also add the entry prefix here. And because it's coming this way, so this OIF is going to point to this interface. So when a packet arrives here, matching the prefix, go on this interface, and coming here, this router is going to forward it similarly down this way, and then coming into the organization 0. So by announcing or advertising the prefix, okay, we also draw the data into the organization, and the data is actually destined for one of the hosts in the subnet anyway. So the routers inside the subnet there, we just we'll be doing further routing there to get to the final destination. Nice. So you see, instead, organization 0, 1, 2, all the way to 7 will be sending one advertisements only instead of these many advertisements. What's even nicer is this, the ISP. ISP doesn't need to send 8 individual advertisements out, just send one. Because it's very easy to aggregate all these, right? Because this is the coarser granularity covering, right? Superset of all these subnets prefix. So there's just one advertisement out this way. One on the link, one on this link, one on this link. Advertisements, the distribution of it, very, very efficient. And so here, the entry is simply 200 something something 6.0, and it goes on this interface. Data matching this will all fit and then go on here. This router here then will split the packet 8 ways, and by checking the destination address of the packet to these 8 different prefixes and see which prefix matched better. So that is the idea, and why we save more bandwidth here. This is the third benefit of doing the prefix matching, in addition to what? Making the forwarding table smaller and the lookup process faster. So the slide here is actually introducing a very interesting scenario. Okay, organization 1 originally here is moved down here to a different ISP. So that prefix advertisement will travel down this way, and ISPRS will try to aggregate it with the original IP address block. Well, ISPRS will find that unfortunately the two of them are not aggregatable. In this case, 2 separate advertisements will go on out into the internet. The forwarding table here will contain 2 entries. One is starting with 199, and one starts 200 dot something 18.0 and 23 bits. This one is 16 bits. And of course, this entry here, okay, will arrive also at the router here at the internet, on the internet. And therefore you have 200 dot something, 16, and 20 here. So this entry is gonna take the packet out this interface. These 2 entries is gonna take packet out here. So if there is a packet coming in that is supposed to go to organization 0, it's gonna match the first entry, isn't it? It's not gonna match the entry number 3 because hey, this address space and this address space, they are actually disjoint. Okay? So not gonna match this guy here. So packet going for destination organization 0 is gonna go down and travel and down to organization 0. So setting up the forwarding table this way, not a problem. Similarly for organization 2 and 3 and all the way to 7. Okay? As long as the destination IP address is matching this, it's going to come down this way. Yeah, I know you're thinking, hey, what if the packet is going for organization 1? You're right, it's going to match the first entry. Ooh, a bit worrisome, yes. But if you look down the table, right, hey, it's going to also match entry number 3. Now, if we call back in section 4.2, what did we say? We're actually not just doing prefix matching, we're doing what? Longest prefix match. So which one is the longer prefix? 20 versus 23. So packet carrying destination for organization 1's machine is going to come down this way here and eventually reaching organization 1. So we're okay, right? So the overhead of sending the advertisements is still very low. Now slightly higher here if it's not exactly aggregatable, but forwarding is going to be fine. And we allow what? Organizations moving from one ISP to another ISP without changing the physical IP addresses. Okay? Therefore, all these servers are running here. They can stay using the same IP address without needing to change the name to IP address mapping. Now, we get the block of IP addresses from our ISP, but next question to ask. How does the ISP get its own block of IP addresses? So it's like saying, hey, the system admin asks the higher level system admin, but higher level system admin asks the even higher level system admin, right? And this goes on. Who's the highest level system admin? Where's the end? Yeah, this organization is the end. So Icmp here is the highest level system admin. This is a non-profit organization overlooking, okay, the allocation of the IP addresses, the allocations of the domain names, and managing also the domain name servers. So very important organization. We normally don't know. Okay, only the people who knows about the internet knows a little bit about Icmp.
All right, so that's all the time we have today. We don't have time to talk about NAT yet, but we'll definitely break open next week's lectures from NAT. With that said, that's all the lecture time, and goodbye. Go get lunch, and in case you have questions, feel free to type them up or call in. Okay, bye. Okay, okay, let me end the stream first. Okay, Catfish, let me end the stream first.